Venus today is a literal hell. Temperatures near 460 degrees Celsius. Pressure dozens of times higher than Earth's, and not a drop of water. But what if things were different before? What if Venus once had oceans, clouds, and even conditions remotely similar to Earth? Today we'll try to recreate Venus's past in the Universe Sandbox simulator and model its journey from paradise to hell. And in the first simulation, we'll have the best version of Venus from the past. I'll completely remove carbon dioxide from its atmosphere, slightly increase nitrogen to 3.5 Earth atmospheres, and add liquid water to the surface of Venus. One Earth ocean. As you can see, Venus immediately got a dense atmosphere again. But that's temporary, guys, you'll see later. And since we have a version of Venus in the past, the sun's luminosity in the past was also lower. The sun wasn't as active back then, and its luminosity was about 0.7 of the sun's current luminosity. For this Venus, a day will be 3 Earth days, and I'll set the average albedo to 0.4. Before starting the simulation, I'll hide the atmosphere and clouds. And well, we can already see these changes on the surface. And now I'm starting the simulation. 3 months are passing per second. As we can see, water is starting to cover the surface of Venus. That is, because of this dense atmosphere, water begins to condense and fall as liquid water onto the surface. Here you can see this whole process, and the temperature is actively dropping already below 150 degrees Celsius. The pressure, as you can see, is also falling rapidly, and time has passed. You can see for yourselves what Venus has turned into. This is how it looks. The average temperature is 35 degrees Celsius, and the atmospheric pressure is just under 4 atmospheres. Next, I'll change its appearance to be more realistic. Since the atmospheric composition has changed, we can add an Earth-like haze to the atmosphere. This looks much better. Now for the clouds. I'll set the first type of clouds to turbulent. Given the large amount of water on Venus, I think these kinds of hurricanes would be quite realistic on Venus. And I'll change the cloud color to these, with more of a yellow tint. And I also changed the color of the oceans. High elevations will be this color, middle ones like this, and low ones like this. I'll increase the contrast to the maximum, or maybe decrease it a little bit. Let's leave it somewhere around here. And I think it wouldn't hurt to exaggerate the terrain twofold, for example. By the way, you might ask, what's that green stuff near the coast? Well guys, those are coastal salts on Venus. Here is a detailed visual of what it all roughly looked like on Venus back then. And now, look at the Venus I have created. Again, this is the best possible version of Venus in our entire video. It'll only get worse from here, you'll see. But I'll save this Venus just in case. Let's call it Venus 1. And now guys, the next simulation. In this simulation, the sun's luminosity will be 0.75. I won't change the albedo. The axial tilt for this Venus will be 45 degrees, meaning Venus has no moon, and it's been tilted way too much like this. Let's imagine that's exactly what happened in the past. But this time, Venus will already have some carbon dioxide, and its amount will be 0.25 of Earth's atmosphere. And there will be less water, about half of Earth's ocean, and a day on Venus will already be 30 Earth days. So Venus will already be slowed down, so to speak. Hiding the atmosphere, the clouds. While the temperature is stabilizing, I want to tell you some interesting information about Venus's oceans in the past. Listen to this. At some point, a key turning point begins. The sun's luminosity grows, and the oceans on Venus start to evaporate faster and faster. It would seem like just more steam in the atmosphere. But this is exactly where a chain reaction is triggered. Water vapor is a very strong greenhouse gas. The more of it there is, the more it traps heat near the planet's surface. The temperature rises, more water evaporates, there's even more vapor in the atmosphere, and the planet heats up even more. This process is called the runaway greenhouse effect, and this is where Venus passes the point of no return. The oceans can no longer cool down and condense back. They literally evaporate completely, turning the planet from a potential paradise into the very hell we see today. And overall, we see that the temperature has settled at 65 degrees Celsius, the pressure has risen and is over 4 atmospheres. And we see that quite a lot of water vapor has already appeared in the atmosphere, which I just told you about. The temperature hasn't reached critical values yet. The oceans on Venus aren't boiling away yet, but as the sun's luminosity increases, the rate of water evaporation will keep growing, and the planet will heat up more and more, restoring the display of the atmosphere and clouds. And with this version of Venus in the past, it looks like this. I'll also save it. I'll call it Venus 2. Now for the next simulation. At this point in time, the sun's luminosity will be 0.8 times its current level. So we're simulating how the sun ages and becomes brighter and brighter. Now Venus's albedo will be exactly 0.5. That is, because the oceans will start to boil, the albedo will increase. The axial tilt will be 25 degrees, so it's already shifting. The days on the planet will already be long, lasting 120 days. So, time has passed, and the sun's gravity is starting to slow Venus's rotation, and the amount of water in Venus Venus's ocean will be halved again. And we immediately see how much Venus's surface has dried up in that case. But that's not the most important thing. The main thing here is that the concentration of carbon dioxide in Venus's atmosphere will specifically start to increase. So here, in this simulation, we'll already have 1 Earth atmosphere of carbon dioxide on Venus. Started the simulation. Look, the temperature is starting to rise. While the temperature is stabilizing, I'll tell you why carbon dioxide starts appearing on Venus, and in significant amounts. Listen, after Venus loses its water, another important process is triggered: the growth of carbon dioxide in the atmosphere. As long as there are oceans on the planet, carbon dioxide is partially trapped. It dissolves in water and is bound in rocks as carbonates, much like how it happens on Earth. But when the water disappears, this mechanism breaks down. First of all, there's nothing left to absorb the carbon dioxide, so it stays in the atmosphere. Secondly, at high temperatures, carbonate rocks begin to break down, releasing previously trapped carbon dioxide. And thirdly, active volcanism continues to pump carbon dioxide out. As a result, carbon dioxide begins to accumulate faster and faster, intensifying the greenhouse effect even more, and it becomes a vicious cycle. The hotter the planet gets, the more carbon dioxide there is in the atmosphere, and the more carbon dioxide, the stronger the heating. This is how Venus finally cements its state as a scorching, dense, and inhospitable world. And here we see that the temperature is 130 degrees Celsius, and the pressure is already 30 atmospheres. We see that the equator is practically without water now. Water remains only at the poles and in the middle latitudes, but that's only with this concentration of carbon dioxide. But what if we make it 2.5 Earth atmospheres? Well, yeah, the obvious things are happening. The temperature continued its upward climb, and water is leaving, roughly speaking, the middle latitudes, and everything remains only at the poles. Well, I think you get it. The more carbon dioxide I add, the more water will leave the planet's surface. But we'll look at the process of total water loss on Venus a bit later in the simulation in this video. For now, let's go back to Venus 1. Remember I saved it? Here it is actually the best version of Venus. Here I'll go back again. The sun's luminosity to 0.7. Here we'll have 2 different models of this version of Venus, but this Venus will have a significantly increased orbital eccentricity. It will be 0.0666. That's the value. In the past, many planets had eccentricity, right? It leveled out over time. So let's run a simulation with an increased eccentricity for Venus. For such a Venus, the axial tilt will be 45 degrees and a day will be 10 days. In this model of Venus, we have almost 1 Earth ocean of liquid water on the surface of Venus. And I'll set the simulator time to 3 months per second and start the simulation, hiding the atmosphere and clouds. In this simulation, because Venus has an increased eccentricity, we can see the effect of these seasonal fluctuations in the amount of water on the surface of Venus. That is, at the point closest to the star, our water will evaporate, and there will be more and more land. But at the point furthest from the star, the planet will cool down, and water will condense back, increasing the number of oceans. So what do we see with this model? We have a temperature of 17 degrees Celsius. The temperature fluctuation isn't as large as expected. And even if we zoom in here, it's not really visible that anything is being flooded or conversely dried out. Well, in general, everything is clear with this model of Venus. We even see ice caps appearing here. Now, I'll make a second model of Venus, and in the second model of Venus, the amount of water will be 0.3 Earth oceans. That is, there will be much less water. Here you see how more land has appeared on Venus. The average albedo here will already be 0.5, meaning it will increase, and there will already be carbon dioxide in the atmosphere. In the first model, there wasn't any, but in the second model, I'll set the carbon dioxide to as much as 2.25 Earth atmospheres. The color of the atmosphere has even changed, hiding the atmosphere and the clouds. But our goal is to find out if, with an increased orbital eccentricity, water will momentarily return to the surface as it cools down, and conversely evaporate more actively as it approaches the star. Well, at the moment, the average temperature is 152 degrees Celsius, and the pressure is almost 50 atmospheres. But let's take a close look at the surface of Venus. As we can see, as it moves away from the star at the furthest point of its orbit, liquid actually returns to these places. And when the planet gets as close as possible to the sun, the liquid in these places evaporates and recedes. So there are these major seasonal jumps in water changes, to put it in very rough terms. I'm zooming in as much as possible. You can see for yourselves water appears here for a moment and then vanishes. This is how water cyclically appears and disappears here on Venus as it moves along its orbit. And here you can already see what Venus is turning into. The atmosphere is already dense, but for now guys, it's mostly saturated with water vapor. But believe me, this water vapor won't stay here for long. Now I'll take Venus from this simulation, from this model, and move on to the next experiment, the most interesting one in this video. video. Now we're going to simulate Venus's path to the modern-day Venus. In this simulation, let's start by setting the sun's luminosity to 0.75. I'll set the carbon dioxide to 5 Earth atmospheres right away, and the albedo will stay at 0.5 for now. I'll adjust the eccentricity a bit because, as I told you, the orbit will level out over time. Let's make it 0.05. And of course, the length of the day will slow down over time. I'll set it to 30 days right now, hiding the atmosphere and clouds. Oh, and I'll also set the axial tilt to 20 degrees. That's it. Look at the temperature. I'm speeding up the simulation. At what pressure can liquid water still exist on the surface of Venus? And with what carbon dioxide composition? The temperature has settled at 222 degrees Celsius. And we see that the water is essentially at the poles. Okay, water can still exist. The pressure is already 76 atmospheres, and now the amount of carbon dioxide in the atmosphere will be 7. At this value, liquid water continues to exist at the poles. The temperature is 250 degrees Celsius. Now I'll raise the amount of carbon dioxide to 8 Earth atmospheres. The pressure is already 84 atmospheres. Crazy. But for now, there's a lot of water vapor in the atmosphere. Liquid water still exists. Okay, now let's increase the carbon dioxide to 10 Earth atmospheres. The temperature is already 287 degrees. And yes, as you can see in my simulation, liquid water still exists here. And it's held by the immense pressure, which is now 92 atmospheres on Venus. We see that the amount of water vapor in the atmosphere is as high as 80 Earth atmospheres, and we see such a very dense atmosphere on Venus. But the temperatures on Venus are already huge. The maximum temperature is 340 degrees Celsius, and the atmosphere is heating up quite a bit from that too. And now I'm gonna tell you about an interesting process that happened in the past on Venus. Listen, when the greenhouse effect accelerates, Venus's atmosphere gets so hot that water vapor rises higher and higher into the upper atmosphere, and there it's no longer protected. Under the influence of the sun's ultraviolet radiation, water molecules begin to break down. Water splits into hydrogen and oxygen. After that, the light hydrogen simply escapes into space. It's moving too fast for the planet to hold onto it. And this is the key point. Water isn't just vanishing from the surface, but forever. Even if conditions change slightly later, it's impossible to bring back the oceans because the hydrogen that makes up water is lost for good. This is how Venus is finally stripped of its water. Oh, and as we can see, the water at the poles has already disappeared. And why did the water disappear? Because the pressure dropped sharply when the water vapor escaped into space. But now let's go back to carbon dioxide, and this time I'll double its amount in the atmosphere to 20 Earth atmospheres. The pressure immediately jumped up to 23 atmospheres. The sun has also managed to become brighter. It now has a luminosity of 0.8. I'll hide the atmosphere and clouds. This is how Venus looks. No water, a desert surface, so I'm just giving Venus back its familiar appearance. And I'll also slow down Venus's rotation to 100 days. And time has passed. The orbit has rounded out even more to about 0.25, and we already see 356 degrees Celsius on Venus. Now Venus will have even more carbon dioxide, 30 Earth atmospheres. The albedo will increase to 0.6. The day will slow down to about 150 days, and the orbital eccentricity will become 0.01. The sun's luminosity will be 0.85. In that case, the temperature on Venus is already 413 degrees Celsius, and the pressure is 32 atmospheres. And Venus's appearance is now practically like the modern one. And actually, a little more time will pass, and Venus will become the one we're used to knowing, with the same pressure and temperature. As we've seen, even small changes in the atmosphere, solar luminosity and so on can completely change the fate of an entire planet. Venus could have been a world with oceans, but in the end, it became the most inhospitable planet in the solar system. If you liked the video, please give it a like and leave a comment. Thank you very much.